welcome. This is a conversation with Dr. Ellison. He is an ecologist, photographer, sculptor, and writer, and he retired in July 2021 after 20 years as a senior research fellow in ecology at Harvard University and as a senior ecologist at the Harvard Forest. Dr. Ellison has both authored and co-authored numerous scientific papers, books, book reviews, and software reviews. He is currently visiting the Universidad Técnica Federico Santa Maria in Valparaiso as a part of a research project. Today we will learn more about some aspect of his career as a scientist and also part of his research and motivations. Aaron, welcome.
Thank you very much, Ronnie. It's great to be here in Chile again.
Sure. Let's go early in your life. What was it about science that interested you the most?
So, science is a way of knowing about how the world works. And early on, I think it was having a way to make sense of the world in a way that was more based on what you saw as opposed to opinions of others that made science particularly attractive. And in particular because I was interested in things outside, things, collecting butterflies, collecting bees, and running around in the woods that is not quite as subject to, at the time for a little kid, subject to sort of the whims of human opinion.
Yeah. Somebody says that science is an organized way to guess. Do you agree with that?
Yeah, that's a reasonable thing to say.
So do you remember the first scientific concept you have learned?
The first scientific concept that I learned, well, if you count mathematics as science and computer science as science, the first two things I remember, I took a programming course when I was probably 8 or 9 years old on weekends at one of the museums in the city. And we learned the programming language APL, which no one remembers anymore, but which stands for A Programming Language. And the very cool thing about it, as an aside, is that the primitives in APL are matrices and vectors. So it's a lot like R, so it made sense that way. And then related to that, probably the first other real mathematical concept I remember learning was base arithmetic. I had a board game that you played in different bases, so I quickly had to learn how to convert between like base 2, base 3, base 10, and what they meant. And so having that window into a world that you could measure things and compute things in different scales was a real eye-opener.
I see. So in college, you completed your degree in Asian philosophy. At that time, did you also have interest in ecology? And actually, how was the transition?
So that's a very common question, and I'll answer the latter in a cryptic way, which is that there's very little space, intellectual space, between the Tao and the intermediate disturbance hypothesis, which will only make sense if you know something a little bit about ecology and a little bit about Chinese philosophy. But the truth of the matter is that I went to college with the intention of studying nuclear physics, particle physics, and pure mathematics. And I got distracted in two directions, which turned out to be much the same direction.
Well, so what specifically made you interested in ecology and evolutionary biology?
Well, there are two aspects to that. Again, there are always multiple aspects. What really got me started in ecology and evolutionary biology as the basic sciences that they are was, as is almost always the case for young, impressionable college students, was an inspiring professor. And I remember the first day of my introductory ecology class, which I took when I was a senior in college, and the professor walked into the classroom. He was a new assistant professor, 2 years then at that point, maybe 3 He was about 26 years old. And he walked into the class and he said, ecology is not about saving whales. And then he proceeded to derive the equation for exponential population growth. So the first day of class, about 50 students had shown up, most of whom thought that ecology was about saving whales. And after seeing the derivation of the exponential growth equation from basic first principles as an ordinary differential equation, 15 of us came to the second class. And so that convinced me that ecology was a really good thing to study. Now, on the applied environmental ecological side, I actually participated in and went to the very first Earth Day in 1970 in Philadelphia, where I grew up, and that probably set me on the career at the time, although I didn't know it.
Okay. So you worked for 20 years in Harvard University. So in those years you worked there, do you remember any curious facts related to your work there?
It's not so curious about the work itself. It's more curious about Harvard as an institution. Harvard is the oldest university in the United States. It's certainly not the oldest university in the world, but it has the idiosyncrasies that go along with being a very old and venerable institution, one of which is that everyone outside in the world thinks that Harvard has this massive endowment and they have all this money that they can spend. But in reality, every department has its own endowment. And when you add them all together, you get a big endowment that Harvard manages. But because of that, every department has to essentially be self-supporting. And Harvard has a mechanism for that, like all universities have, where you have to have account codes for transferring money between departments and things. We all do this. But at Harvard, those codes are called TUBs, T-U-B-S, which doesn't stand for anything. It's because every tub has to float on its own bottom. So every bathtub has to float by itself. So I thought that was one of the most interesting things to learn about Harvard. It's one of these trivial things that no one else really cares about.
So do you remember anything funny that happened to you at work?
No. No, that's why we call it work. Funny happens outside of work. We all play practical jokes on our students, of course, but they happen to my students, not to me, so it doesn't really count.
Okay. If you look at your research projects throughout your career, is there one in particular you like or that is special in some singular sense?
Well, they're all special in their own way, and one of the great things about being an ecologist and studying natural systems is having the opportunity to travel all over the world and learn about different systems all over the world. But when I think about what's really a perhaps quirky, interesting story, when I moved to Harvard, I had just started working on carnivorous plants. Just started about a 25-year study of what ended up being about a 25-year study of things about the biology of carnivorous plants. And at the time, the first thing I wanted to find out, one of the first things I wanted to find out was what the carnivorous plants were eating. And it turns out that they mostly eat ants, at least these pitcher plants did. And so I ended up learning a lot about ants as well. That's a whole story for another day. But I have a collaborative project in Germany related to forest ants that build nests that are very large mounds. And these mounds can be 1 meter to 1.5 meters high and maybe 3 or 4 meters in circumference. And that's what you see above ground. So these are really big, like bigger than this table, bigger than either of us sitting here. And there were two interesting things, particularly interesting things about studying these with my colleagues in Germany. The first is that my colleagues in Germany are geologists, and they were interested in the phenomenon that these ants make their nests along active fault zones where it's just a little warmer where there are earthquakes. And often the ants will build nests where the geologists hadn't mapped fault zones before, and when they saw the ants there and they looked more carefully at the geology, they would find fault zones. And so there's this idea that they could be used as a good geological indicator, which is really fascinating. We were interested in the spatial pattern of these on the landscape and actually demonstrating that there was this strong spatial relationship between the positions of the ants and which is a point process, and the lines of the earthquake faults, of the tectonic faults, which turned out to be a complicated problem in its own right, but had a twist to it that we automatically assume when we go out to sample a process like this, and we'd go to an area and we'd say, we're going to sample all the ant nests, that you can actually sample all the ant nests. I had the idea in this project based on other work that other ecologists had done with other organisms, mostly animals that are moving around when you're trying to count them, that you don't detect them all. And so you need to incorporate into your models of population size or population abundance or spatial pattern the probability of detection. So I said, well, what's the probability of detecting one of these ant mounds? Now, if you're walking around in a field or a forest with ant mounds that are 1 meter high and 4 meters in circumference, and they're bringing up soil from underground, and so they're different color to landscape, you'd think you'd walk around and you'd encounter every one of them. And the probability of detection would be 1. So we did the experiment. We got a bunch of students in, and we had them map, each map independently, about, I forget how many plots it was, maybe 50 plots, 100 plots, each about 30 meters on a side, if I remember the right size, and count and geolocate all the ant nests. And then we had the ant experts do the same thing. And we looked in and computed the detection probability, which for the students who had never done this before was about 20%. For the experts, it was only about 50%. That was completely surprising. How do you miss half of them? So we wrote a very nice paper about that and then factored the detection probability into the other estimation, which turned out to be significant and interesting of itself. But the idea that detection probability of something that doesn't move is as low as things that are running, like lions and cheetahs and things like that, was completely astonishing to us.
So I remember I saw a video when you explained why ants are important. Can you tell us briefly why they're so important?
Well, first off, there are so many of them. A recent study out of Australia estimated that for every, I'll get the numbers wrong, but for every person on the planet, there are tens of thousands of ants. So there are trillions of ants running around on the planet, and there are only billions of people. So they're everywhere. You're probably never more than a couple meters from an ant, even in this building where you're not seeing them. They are really important at breaking down and decomposing dead things. And things are dying all the time. Animals, insects, plants are dying all the time. And if we didn't have all these decomposers around, we'd be knee-deep in carcasses, and we're not. Ants do that. And then they make soil for us. They're constantly turning over the soil. So no ants, no food, no farms, no soil, nothing to grow in. So they're important in so many different ways.
Great. Considering your career as an ecologist, what are the most important lessons you have learned from your experience that also can be applied to by environmentalists?
I think probably the most important lesson that I take is that we don't know very much. We think we know a lot, and we think that we know so much that we can manage the environment. And we don't know that much, and usually our management doesn't work very well. And so the primary lesson I take is be a lot more humble about what you think you know and what you think you can do.
Great. So if you could go back in time, would you choose the same field of research?
If I could also go back to 1978 and do it again, probably yes. You know, and not know what I know now. Right? You know, there's always that paradox of time travel. But probably yes. I might have also, you know, if I could do it all over again, I might have tried a little harder to stick with pure mathematics. I got hung up with topology, and I didn't go any further. So, but maybe.
Yeah, let's talk about climate change. What can governments do immediately to mitigate the effect of climate change?
So there are there's a key assumption there, which is that climate is changing now, but it didn't change before. And so we have a problem to manage. What we're really managing is the rate, or worried about is the rate of climate change. So that is faster now than we have evidence for in the past. And so managing or mitigating the rapidity is really the issue here. If you look, let me step back and say governments are part of the solution. They're not as much of a problem as people think they are. The problem is the system and the multinational corporations that transcend what individual governments can do. I often I gave a talk about climate change a number of years ago to students who at the Yale School of Forestry and Environmental Studies, which is now the Yale School of the Environment. One of the students asked me this question. I said, my response was, you're at Yale. You have all these connections, all these networks. What you really need to do is get on the board of directors of ExxonMobil or become the CEO of a large agricultural multinational and change their culture. What they want to do is go out and protest and study ecology and grow trees or whatever. But really, we have to address the fact that 90 companies, 90 multinational companies are responsible for 90% of the carbon emissions and the water pollution and the mining and all of these things. So if governments are going to play a role, governments have to regulate these industries and say, we have a target and it's not voluntary compliance. You have to do this if you're going to make a difference. We don't do that. That's not embedded in sort of early 21st century laissez-faire capitalism. So we don't do that. But governments need to regulate more and cooperate more.
So you have visited Chile many times and know our country pretty well. Can you give us your perspective about what could be done here in terms of environmental policies?
So let me start by saying I've visited Chile and here 4 times, and it is one of my favorite countries on earth. If I were able to live somewhere else, I would probably choose to live here. It is just really, honestly, one of my favorite countries.
You're always welcome here. Yeah.
You know, it's just great. Chile is very good about participating in global environmental initiatives and signs on to various treaties, and ensures that its industries are in compliance with international environmental standards. So it's very outward facing, which is in line with Chile as a producer of lots of products that are exported and lots of raw materials that are exported. You could do more here internally. You know, it's great that there are no single-use plastic bags, but it'd also be great to get the diesel trucks off the road and to get the diesel cars off the road, and there'd be more electrification, more, you know, from an environmental perspective, one of the biggest challenges here is water. Right? Chile is a very dry country, and it's part of its geography. You're not going to change that. But water use and water purity is a problem here. And as an example, and we're all in the United States this time of year, almost all of our produce that we get in the supermarkets is coming from Chile. Right? So I can go into the market and I can get a Chilean avocado now at home, just like I can get a Chilean avocado here. Well, producing one Chilean avocado for the export market takes 350 liters of water that would support that same 350 liters of water is what about 7 people need to live on every day. And so managing that in an environmental context is a big challenge.
Yeah. Right. So what do you think is the role of universities in this respect?
So I think the role of universities, you know, what we do as academics and scholars is we provide the most reliable data with which policymakers and decision makers can do their jobs and make decisions. At the same time, we can be strong advocates for using these reliable data. We often say that scientists are just objective. And so we do our experiments, we push out the data, and someone else's problem to do with it. But you'd never ask someone who, like an art historian, to say, well, I study Michelangelo's sculptures, or I study Dali's paintings. You can do with them whatever you want. No, you're going to advocate for their preservation, for their restoration, for their repatriation, for all the things that you would do with this knowledge. Well, we should be doing the same thing with the results of our science. There's no guarantee if you have a seat at the table and you can contribute to the decision making that your voice will be where the decision goes. But you need to be at the table advocating for your position. And I think scientists don't do that enough. And scientists working in universities need to do that, and universities need to support their scientists and their faculties in general to do that.
So in terms of academic work, do you think that publication of articles will continue to be important for professors, PhDs, and postdocs?
Well, I'd like to say yes. I've been a senior editor or an editor-in-chief of ecological journals for almost 25 years now. And so I have a vested interest in saying that papers are what you should be doing. But the reality is that with preprint servers, social media, and the like, that the publication in a journal becomes the archival piece of record. But more and more we're looking at preprints and altmetrics and other ways of evaluating scholars' activity, how they communicate with the media, whether they have a seat at the decision-making table. It's much more of a mix now than simply writing articles or the occasional book.
So do you have a message for young statisticians and ecologists about what is important for their career, academic careers?
I think the most important thing is to have a life, that to keep in mind that your work is not everything in your life, and that you don't actually get that much more done working 80 hours a week than you do working 40 or 50 hours a week. So take time for life too. Your work will still be excellent.
Good. Can you share with us a couple of your favorite books?
So there are two that come to mind. One, and they're both in the science fiction vein. I grew up reading a lot of science fiction, and that's still where I go for both entertainment and thought. So a book published in 1959 written by Walter Miller called A Canticle for Leibowitz. And it tells the story of a Christian order founded after a nuclear disaster, trying to keep and preserve the knowledge of what's left of civilization for the next time. And the novel goes over about 3,000 years of sort of this repiecing together of the scientific knowledge of humanity, only to, of course, have it evaporate again in another nuclear cataclysm in 3,000 some years in the future of the book. And of course, I grew up, I was born before the Atmospheric Test Ban Treaty and before the Non-Proliferation Treaties, so I grew up in the shadow of nuclear weaponry, and of course we think about this again now. The other, again, the science fiction published even earlier. It's the original publication was as a short story, a novella. It was later turned into a novel. But Isaac Asimov wrote a story in 1941 called Nightfall, and the premise of the story is a quote from Ralph Waldo Emerson in the 1800s, and I apologize for reading it. Emerson said, "If the stars should appear one night in 1,000 years, how would men believe and adore and preserve for many generations the remembrance of the city of God?" And the editor of Astounding Science Fiction, John Campbell, in conversation with Isaac Asimov, said, "No, I think if the stars appeared once in 1,000 years, people would go crazy." And so that was the genesis of this story, and Asimov took that idea and wrote a story about a planet with 6 suns where the sun never set. It was always light. And so people had this irrational fear of the dark, and they didn't know what to do with it. But the scientists discovered that about once every 2,000 years, there was a giant fire all over the planet. Everything was wiped out. Another one of these, we have to rebuild civilization stories. And they worked through the calculations, and they realized that, well, there's this moon up there. And once every 2,000 years, when there's only one sun or one of the 6 suns up, also this moon comes into conjunction. We have a total solar eclipse, and the planet goes dark for half a day. And they hypothesize that everyone goes crazy, lights fires because they're scared of the dark, and they burn the whole planet down. They have to start over again every 2,000 years. And so they talk about this, they publicize this, they're good scientists, just like the recent movie, Don't Look Up. If you haven't seen that, it's a great movie. No one believes them. Everyone goes on with their lives. And then the eclipse happens, and all the stars come out because they're in the middle of a nebula. And all the stars come out, and everyone goes crazy, lights fires, and the whole thing burns down. And he does this in like 40 pages, this story, whereas Walter Miller's novel, which is really a similar theme, is a whole novel, although he wrote it in 3 pieces. But It's a remarkable story about both of them, about the importance of science in preserving how we understand the world, how we think about the world, how we recreate the world, and how there are only this many scientists for all the people in the world, because really most people aren't scientists. And so part of our job is communicating the beauty, the wonder, and the value of science to other people.
And this was not prepared, but as a photographer, do you have a favorite picture?
As a photographer, do I have a favorite picture of mine or of somebody else's?
That you took? Yeah.
I have lots of favorites of mine. I've recently been doing some photography of bristlecone pine trees, which are the oldest oldest individual organisms on the planet. They live up to about 5,000 years, and they're in very remote mountaintops in southeast. But I will say that a photograph of mine from 2016, when I was in Valparaiso, was just in a gallery show in Vermont. So that's one of my favorites right now.
Okay. Finally, if we try to summarize the 21st century in just one word, what would that word be?
That word would be chaotic.
Chaotic.
But chaotic in the mathematical sense of sensitive dependence on initial conditions, not chaotic in the popular sense of it's just crazy.
I see. Well, it has been a great opportunity for us to have this conversation with an expert in ecology and environmental sciences. We would like to thank Dr. Ellison for kindly agreeing to this interview. We would like also to thank the Fulbright Specialist Program through Fulbright Chile for funding the visit of Dr. Ellison to Chile, the Advanced Center for Electrical and Electronics Engineering, AC3E, for support, the Mathematics Department, and finally, the Department of Online Education of Universidad, Técnica, Federico, Santa Maria. Thank you very much, Aaron.
Thank you. It's been a pleasure.